go on my computer. And now we should be recording now. So, okay, we're going to begin something that I know that you've covered in high school, but I really would like you to just delete everything you already know about how to do um, stoichiometry problems and learn the method that I'm going to show you. It is much simpler. Please believe me, it is. And I will try to explain it as we go along through here. Then we'll work some examples with it. And I believe this probably is the last topic on our before our exam 3 on Monday. So I'll review what we haven't covered. We'll talk about that on Friday if we have missed something. And then also on Friday, we will uh, go over the practice exam. So I hope you will work through that before Friday, and then we can be more efficient. We might not have time to work the whole thing through on Friday, so I can just work the ones that you've had trouble with first. Okay. All right. So now, when we talk about a chemical reaction, we're talking about atoms and molecules and ions that are involved in the reaction. And the unit that we use to count anything is the mole. Now, if you remember, a mole is 6.02 times 10 to the 23rd, Avogadro's number, of whatever it is. So it's a count of the number of particles, just like I say a dozen. I don't have to say a dozen eggs. I could say a dozen apples or a dozen oranges. The dozen is 12, doesn't matter. But apples and oranges and bananas and eggs all have different weights. And that um, that was my um, don't lose your phone app. Whenever I'm using my Wi-Fi real heavily, and my little finder for my phone tells me to go, I've lost my phone. So I've clicked it off, but I'll leave the little thing out where I can get a hold of it in case it happens again. Okay, so the point is, a mole of anything is Avogadro's number of those things. And those things have different weights and different characteristics, but a mole is a count. A mole of atoms, though, is a count of the number of atoms present, but atoms are so small, you could never, ever count them. Now, let's think of, suppose you're in a factory on an assembly line, and your job is to make sure there's 144 paper clips, 12 dozen paper clips in a little box that you're going to sell. Are you going to sit there and count out 144 paper clips and then close the box and get the next box and count out 144? No. What will happen is that little stand in front of you will come down the line. It'll have a box sitting on it that's already been teared out on the balance. You'll put 144 paper clips in it once. You do have to count the first one. Somebody had to count Avogadro's number. So you have to count the first one, and you then close it up, set the box on the output line. Now, the next box that comes down, all you're going to do is pour paper clips in until it weighs the same as the other one did. Then you know you put 144 paper clips in. That's sort of the way we count atoms. We count them because this particular value of Avogadro's number, 6.02 times 10 to the 23rd, is a number that gives you that many particles will have a mass equal to the atomic weight of the element. So when you when you look at your periodic chart and you look on the periodic chart, say if we're looking for hydrogen, you can't see it on there. I don't think it's built up, can be blown up enough. but it says 1.01 is the atomic mass of hydrogen. If you take 1.01 grams of hydrogen, that will be 1 mole of hydrogen, and it'll have Avogadro's number of hydrogen atoms in it. If I look at the next element below it, lithium, it says 6.94. So 6.94 grams of lithium would have Avogadro's number, 6.02 times 10 to the 23rd lithium atoms. So a mole of any substance has a mass equal to its atomic weight in grams. So we count atoms by actually weighing them, just like the guy in the assembly line counts paper clips by weighing 144 paper clips. Now, if we're talking about molecules, a mole is still the same, and it's made up of atoms. So if I took water, H2O, it would have 2 hydrogens for each oxygen, but the water molecule would contain a mole of that. 1 mole, Avogadro's number of water molecules, would have 2 moles of hydrogen. That's going to be 2 times 1.001, and 1 mole of oxygen, and its oxygen's atomic weight is 16 on the periodic table. So the molar mass of water you get by adding up the atomic masses that are in the formula, the compound. So in water, a mole of water would be 18 grams. Now, how many atoms of aluminum are there in 5.3 millimoles of aluminum? Well, we've got 5.3. Milli is 10 to the minus 3. That's the way we always do unit conversions within the metric system. Replace the letter or group of letters that represent that unit and replace that with what it's equal to. So milli is 10 to the minus 3. I can convert 5.3 millimoles of aluminum into moles of aluminum just by changing the milli to 10 to the minus 3. So I've got 10 to the minus 3 moles of aluminum. Now I want to do a conversion. How many atoms would that be? Well, I want the unit mole to cancel out. So my conversion factor is going to have moles in the denominator. I want to go to atoms. And now my question is, do I know a number of moles for which I know the number of atoms? Yes, 1. 1 mole of anything is Avogadro's number of those things. So when I do my math, I've got the conversion factor. So 5.3 times 10 to the negative, 5.3 times 10 minus 3 moles of aluminum would have 3.2 times 10 to the 21st atoms of aluminum. So this is how we manipulate moles and atoms. What about the mass? What is the mass of 3.2 times 10 to the 24 molecules of sulfurous acid? Okay, a couple of things. If you don't know what sulfurous acid is, you can't work the problem. So that should remind you to be sure you know nomenclature. It's going to get much more important. I just noticed when I made out my Gen Chem 2 exam yesterday, I did not give formulas for anything on the whole test. I gave names. So this is going to be something you need to know now, and you need to keep for Gen Chem 2 when you take it. Okay, let's set the problem up. The way we set up a problem, here is the given amount, and there's the unit that was given. We want to get rid of that unit, so we want to put moles of sulfurous acid. Formula is H2SO3. And we want to then go to grams. And the question is, do we know a certain number of molecules for which we would know the mass in grams? Yeah, Avogadro's number. If I have Avogadro's number, I'm going to have Avogadro's number, twice Avogadro's number of hydrogen atoms, and the atomic weight of hydrogen is 1.01. I'm going to have 1 sulfur, atomic weight is 32.06. We look at our periodic table. And the atomic weight of oxygen, of course, is 16. So if you add all that together, you come out with 82.09 grams of sulfuric acid is that many molecules. Now notice I did my conversion factor once. I didn't do two chain conversion factors to do that. And this is another thing that will speed things up for you if you'll remember to do that always. The setup is going to be just like this. You have a given quantity with a given unit. Copy that unit in the denominator. If it's in the numerator over there, copy it in the denominator so it would cancel. Put the unit the problem is asking for, what mass of sulfurous acid. So I put that unit up there. And now I need to put two numbers in for which the amount in the numerator is identical to what's in the denominator. And that's what I've done. 6.02 times 10 to the 23rd molecules does weigh 82.09 grams. So the numerical value of that conversion factor, including the units, is 1. The numerator is equal to the denominator. And so whenever you divide something by itself, you get a 1. So when I do my math, I can cancel out the units that I wanted to get rid of. And so I get 440 grams of sulfurous acid would be the mass of 3.2 times 10 to the 24th molecules of sulfurous acid. Now, how many atoms of oxygen are there in 13.2 grams, a 13.27 gram sample of sulfurous acid? Okay. Sulfurous acid is H2SO4. We calculated the molar mass to be 82.07. I have 13.27 grams of sulfuric acid given in the problem. There is the mass given, 13.27 grams, and there is the unit for sulfurous acid there. It's that many grams of sulfurous acid. All right, so I want to put in the denominator a factor that will cancel that out, and I want the mass of, or the atoms of oxygen in the numerator. Well, if I've got 82.07 grams of sulfurous acid, that's a mole, I'm going to have 3 moles of oxygen atoms. So that's going to be 3 times Avogadro's number. Again, now the numerator represents exactly the same thing that the denominator does. We cancel that out, do the math, we get 13.27 grams of sulfurous acid. Would have 2.92.
Dr. Pearson?
Yes?
I'm sorry, where did you get the 3 from again?
I'm sorry?
Where did you get the 3 from?
Oh, the formula has 3 oxygen atoms in it, see?
Uh-huh.
So,
okay.
So I'm going to have 3 times Avogadro's number of oxygen atoms in a mole of the compound. Okay? Very good. All right, now here's a checkpoint for you to practice for your own on this. It may or may not be the one that's on D2L, but what you're looking for is segment 11, checkpoint 1. And you really ought to work that out. You really ought to work with your peer, the rest of the class, in the discussions section of D2L to discuss it with other people to see if you're all getting the same answer and things like this. It's critical you know how to do these, because I think you've seen already the checkpoints give you probably the best indicator of what the quiz or exam might be like. So be sure you can do these. Okay, now determine the empirical formula of a compound that is 32.4% sodium, 22.5% sulfur, and 45.1% oxygen. Now, I'm going to work these problems different than the way you did it in high school. Doesn't really matter much. One way is about as quick as the other one, but I wanted to show you a method that is based exactly on the way we did the other problem. If I gave you a formula of sodium sulfate, we've already figured out how to do the percent composition. We took the mass of the element in a total formula of the compound, and we divided the mass of the element by the formula weight of the compound multiplied by 100 and got percentage. We're going to work our problems like this the same way. So I've got a compound that I don't know, but I do know it contains only sulfur and sodium and oxygen. So I'm going to write the formula NaXSYOZ, where these little subscripts are numbers, but we don't know what they are right now. So what we're going to do is do this. The percentage of sulfur would be X atoms. The atomic weight, I'm sorry, sodium, I said sulfur. The percentage of sodium is X atoms of sodium in the formula times the atomic weight of sodium is 22.99, but I wrote it 23 here. That's close enough. 23.00 really. And we divide it by the molar mass that we don't know. I know that. And we multiply it by 100. When we do that, our result is going to be 32.4%. That's what was given in the problem. So this represents, if I just knew what the molar mass was, I could calculate that. But I could use this to calculate the molar mass if I needed to. But I want to show you, I don't. I need to get X before I could do that. But now let's look at the percent sulfur. How would we set it up? Same way. There's Y sulfur atoms. The atomic weight of sulfur, again on the periodic chart, if I look at the periodic chart, it's 32.07, so 32 is close enough. I would need to divide by its molar mass of the compound and multiply by 100. If I knew Y and did the math, I would get 22.5%. That's what was given in the problem. Now look what happens if you divide these by each other. Then if you divide the percent of sodium by the percent of sulfur, you're going to get some cancellations. The molar masses will cancel out. The 100s will cancel out. So you're left with 23x over 32y is equal to 32.4 over 22.5. We can cross multiply. We get 23 times 22.5 times x will equal 32 times 32.4 times y. We can do the math, multiply those out, divide both sides by the smaller one, and you get 1x equals 2y. So we've seen this before when you get something like that. So if x is going to be equal to this value and y is going to be equal to the multiplier in front of x. So x is going to be 2 and y is going to be 1. So I can now go back and put that into my formula up here. And now my formula is Na2S1OZ. So all I need to get the formula of the compound is what is the value of Z? Well, I'm going to do sodium just like before, but now I know there's 2 sodiums. So 2 sodiums times 23 divided by molar mass times 100 would be the percentage, and that percentage is 32.4. So right there it is. Now, the percent of oxygen would be Z, which I don't know yet, times the atomic weight of oxygen is 16, divided by the molar mass and multiplied by 100. Now, divide these two out. When you do that, of course, molar mass cancels, 100% cancel. We get 2 times 23 divided by 16 times Z is 32.4 times 45.1. I can cross multiply. Now this time I can solve for Z. So I take these numbers and divide by these numbers. So if I do that, I come out with 4. So my formula for my compound is Na2SO4. Okay, let's look at some others. Here's a compound, again, with aluminum and sulfur. Again, I'll set it up the same way. I have X aluminums, Y sulfurs, and Z oxygens. So I'm going to ratio these percentages. And what that's going to be is, notice what I've done. Sulfur's on the top, and I want the sulfur values to be on top. So sulfur, there's Y of them, and the formula weight, atomic weight of sulfur, again, if you look on the periodic chart, is 32.07. So, and then the sulfur, aluminum percentage was 28.1. So for did I do that wrong? No, I didn't. Sulfur's 28.1. That's right. But the aluminum was 15.7. Okay. Now, again, the molar masses and the 100s cancel out. But look at the symmetry. All the sulfur data is in the numerator, and all the aluminum data is in the denominator. And then that's going to give us a structure we can get to very quickly. Cross multiplying, you get this. And multiplying these two numbers out, you get that. And these two, you get that. The smaller number is this one. So 1.5x divided both of them by 505 equals 1y. And so I want whole numbers, not fractions. So I double everything. I get 3x equals 2y. Now x is 2 and y is 3. We want these coefficients to always be whole numbers. Okay, so my formula at this stage is Al2S3OZ. Okay, now to get the Z value, we're going to ratio two others out. And now I do want you to understand the structure and the format. Remember what we're doing. I've got the sulfur stuff on the top, and now I know sulfur is a 3. I've got the oxygen stuff on the bottom, and it's a Z down here. I don't know what it is, but I know its percentage is this. So all the oxygen stuff and all the sulfur stuff is here. Now we can just solve for Z. Cross multiply 16 Z times 28.1 will equal 56.12 times 32 times 3, 32.06 times 3. And do the math. Solve, you get 12. So my formula is Al2S3O12, but you'd probably recognize it a little bit more like this. This is 3 sulfurs and 12 oxygen, but this is clearly aluminum sulfate. So this is a good formula, and it works out fairly simply when we do it like that. Now, let's do empirical formulas for a more complex one. Now, one of the things I want you to remember is we're only going to do that ratioing part with two unknowns once. And then we're going to always use one of the elements we just did and got a number for to do the ratios for everything else. So watch that pattern as we set it up. Now, I couldn't use X, Y, and Z. I could have used W, X, Y, and Z, but I changed to A, B, C, and D for the coefficients for this compound. So it's got uranium, oxygen, tellurium, and fluorine in it. Okay, the percent of uranium is 14.26. The percent of oxygen is 40%. Of oxygen is 5.75. Now, in the formula, this is the atomic weight of uranium, and uranium is way down here, 238.03. And there's A of them in my formula. Looking at the oxygen, there's B of them in my formula, and its atomic weight is 16. So again, I'm going to put the uranium stuff in the numerator, the oxygen stuff in the denominator. Now, it really wouldn't matter which one you did, but I'm going to always go in this pattern. And usually, although I didn't in the last problem, but usually I'll solve for this first element in this step. If we go through and put it together, we get divide this number by this one, you get a 6. So 6A is 1B. So A is 1 and B is 6. So I know these are my formula. My formula now is U1O6. Now, if I want to get the next one, I'm doing uranium again with the next element. It's going to be Te. So this is the percentage of uranium numerator. There's one of them, and that's its atomic weight. This is the percentage of tellurium. in the compound, and there's C of them in there. And if you find tellurium on the periodic chart, its atomic weight is 126.7. Right there. 127.6. Oops, transposed digits again. Okay, but there it is right there. All right, and now we cross multiply, solve for C. C is 6. So now I know 3 of my subscripts, U1, O6, Te6, but I don't know what the subscript for fluorine is. Now I'm going to again ratio uranium with fluorine. Now I'm doing it this way when I have a complex formula, so I can't get all mixed up. If I did this one and then this one, this one and this one, then this one and this one, there's always a chance you'll mess some stuff up. So I'm going to do this one with this one in the first step, and I'm going to do this one with this one in the next step, and this one with this one in the third step. That way I'm sure I didn't make a mistake. So to get the fluorine values, I know uranium's percentage is that. There's 1 of them. Its atomic weight is 238. Percentage of oxygen, of tellurium, I'm sorry, is 34.14. There's D of them, and the fluorine atomic weight is 19. Fluorine right there. Yeah. Okay. Now, cross multiply, solve for D, I get 30. So there's my formula, UO6 Te6 F30. So it's a very complex fraction. And if you do the method you learned in high school, with big coefficients like this, you can round them off and screw up the whole thing and get the formula all wrong because of the round off error that you could have. This is a much better way, and it's really quicker for a very complex reaction, I think, because we've got a pattern we can set up. We can do it very quickly and get to an answer. Now, the final product is this. It's UOTEF56. And I just happened to run across that compound in a textbook once, and I thought, hey, this would be a good one to use as an example in how to do formulas from percent composition. Now, one other problem, sometimes books give you a problem like this, because the empirical formula and the molecular formula are often not the same thing. When you get a formula from empirical formula, from percentages, you get the empirical formula. So the real molecular formula is always a multiple of that. It's 1 times that if it's the same, or it's 2 or 3 or 4 or 5 times the empirical formula weight. So here's my compound. I did use W, X, Y, and Z here. Now, I'm going to take the 33.8% carbon. There's W carbons, the atomic weight is 12. 1.41% hydrogen. There's X of them, and the atomic weight's essentially 1.00797 to be precise. Cross multiply, rearrange, and solve. And you get X, W is going to be the coefficient in front of X, remember, it's a 2, and X is going to be the coefficient in front of W, it's a 1. All right, so the formula is C2H1NYOZ. And then I'm going to find, well, what would be the value for the Y? So I'm going to ratio the carbon again. Carbon is this percentage. There's 2 of them. Atomic weight is 12. Percentage of nitrogen is 19.7. There's Y of them. Atomic weight is 14. Solve for Y. Y is going to be 1. So my formula at this stage is C2H1N1. O. I don't know what Z is. Let's continue. Now I'm going to ratio the carbon again with the oxygen. So 33.8%, 2 carbons in the compound. Atomic weight is 12. 45%, 45.1% oxygen. There's Z of them. The atomic weight is 16. I cross multiply, rearrange, solve for Z. Z is 2. So my formula for my compound is C2H1N1O2. But that's not the molecular formula, because when I add all that up, I get an atomic weight of 71. But the problem told me the atomic weight was actually 213. So 213 is exactly 3 times 71. So this formula needs to be multiplied by 3. So the formula is C6H3N3O6. By the way, I think that's probably trinitrobenzene, I would bet you. All right, here's a checkpoint on that. Again, here's some problems you can work with on your own. Okay. Now, this brings us to the next part of today's lesson, and we won't get completely done. We'll finish up what we don't get done on Friday, and then that won't take long, and then we will go on to review the practice exam that is scheduled for Monday. Okay. Now, we're going to use the concept of Avogadro's number being a count in order to solve chemical problems, and we're going to do this from our balanced equation. Now, if you have learned grams to moles, moles to moles, moles to grams, wipe that out of your head right now. I want to show you a better way. Remember, an equation is a balanced equation because it has accounted for all of the atoms that were in the reactants are also present, exactly that number in the product. So if I can count atoms on the two sides and make those two counts be the same, then that's going to be the balanced equation. So a balanced equation gives the mass of each reactant and each product that's present. All we have to do is do the formula weights. When you balance an equation, it gives the amount of every other substance if the amount of one of them is known. For example, when you do a balanced equation, it's got aluminum and bunches of other stuff. If I know there's 2 moles of aluminum on the left, I know there has to be 2 moles of aluminum on the right. And I can probably use that information to balance the equation. So once you know the amount of one substance in a reaction, you know the amount of all the substances in the reaction. That's going to be really, really important. Now, unfortunately, stoichiometry is often listed as the most difficult aspect of freshman chemistry. If you ask anybody that's had freshman chemistry, what was the hardest part? They'll probably tell you, oh my goodness, it was those weight problems. They're called stoichiometry. Now, the reason why it's hard is this. People are not very successful at getting the right answer. So it appears hard to them. And it's caused by the way it's presented. It's presented as a series of ordered steps. There's going to be 3 steps. You must do step 1 before you can do step 2 or 3. You must do step 2 in between 1 and 3. And you must do step 3 last. The steps have to be ordered for it to happen. So if you go from mass to moles, moles to moles, moles to mass, that's the way stoichiometry is taught almost everywhere. Okay, so that's not what we're going to do, because suppose you've got a sequential process that you have to convert mass to moles. Now, that's a reasonably easy problem, but suppose you had a 50% chance of getting that right. And then you have to convert the number of moles of one substance to the number of moles of another substance. And in a lot of cases, 50% would be pretty good for most people. And you have a half the odds of getting that one right. And then you have to convert moles back to mass. easy problem, but suppose that was also 50% probability of getting it right. The probability of getting all 3 steps right is 1/2 times 1/2 times 1/2. That's 1/8. So just from statistics alone, you got 1 out of 8 chances of getting it right, whereas a 1-step problem, you would have had a 50-50 chance. So this is why it looks so hard to everybody. Now, and it's memorization. You may think you're really understanding stuff, but that's not really what's going on. You memorize, do this step first, then do this step, and then do this step. And if all I've got to do to mess up a memory of someone who's learned something by rote memory is tweak the problem a little bit so you can't do it exactly like that. And then it's going to be hard. And then sometimes it's taught like just a mathematical exercise, ratio and proportions. This is to this as that is to that. That'll generally work, but the problem you run into is you don't have units anymore. They're going to cancel out. And you're going to wind up then with a good chance of missing it. Now, let's look at another way. We're going to do it strictly, we're going to do stoichiometry strictly from the balanced equation. I'm assuming you can all balance equations now. Now, first of all, we made you put whole numbers in the balancing coefficients and made you put them in as the smallest set of whole numbers so that when I grade a class of 100 students, I don't get 100 different right answers. But the truth is, if you multiply that balanced equation through by any number you want to, even fractions, it's still balanced. So you don't really have to have whole number coefficients in order for the equation to be balanced. You can use even decimal fractions for coefficients. Here's an example. Aluminum does react with hydrochloric acid to make aluminum chloride and hydrogen. This reaction will certainly take place, and these are the correct balancing coefficients. Now, I want you to understand, this is telling me I've got 2 moles of aluminum. Well, 2 moles of aluminum chloride does contain 2 moles of aluminum. It is balanced. 6 moles of hydrogen. 3 moles of H2 would still be 6 moles of hydrogen atoms. So it is balanced like that. But that 2 moles of aluminum also means 2 times 27, the atomic weight of aluminum right here, 26.98. So that equation is showing 26.98 times 2 grams of aluminum in it. So it is giving masses in that balanced equation just the way it is. Okay. Now, some other ways we could balance it. Let's double all the coefficients. So if I double all the coefficients, this is what I get. And it's still balanced. See, there's 4 aluminums and 4 aluminums. There's 12 hydrogens and 12 hydrogens and 12 chlorines and 12 chlorines. It's still balanced. It's not the way I would want you to turn it in when we did balance equations, but it is still balanced. I could divide the coefficients by 10. And I would get this. Now, I certainly wouldn't want you to turn that in as a balanced equation, but it is balanced, but it can't be interpreted in terms of atoms. You can't have 2/10 of an atom, but we don't really count atoms anyhow. We can certainly have 2/10 of a mole, and 2/10 of a mole, that's still balanced. 6/10 of a mole of hydrogen, that's still 6/10 of a mole of hydrogen. Everything is still balanced, even though I divided it by 10. Multiply all the coefficients by 0.135. I just made that one up. Okay, but there's what you get when you balance it. It's still balanced. Oh, now, we could do all of those at once. Double all the coefficients, divide them by 10, and multiply by 0.135. And this is the set of coefficients. It's still balanced. See, I think I'm beating a dead horse, but I do want you to see that it remains balanced no matter what you do to the equation, as long as you do it for everything in the equation. And each one of these balancings gives us a different number of atoms and mass. Look, 0.054 moles of aluminum. Well, you take the 0.054 and when you multiply that by 26.98, that gives you the grams of aluminum now shown in this balanced equation. It would still be that many grams of aluminum in this many moles of aluminum chloride. It would still be balanced by mass as well. All right, now we're going to do some problems. Here's a problem. How many moles of hydrochloric acid are required to react with 6 moles of aluminum? So let's think about what we want. We want the equation here to show 6 moles of aluminum. That's what it says, 6 moles of aluminum. What would I need to do to get 6 moles right here? I just multiply everything by 3. Okay, so I rebalance the equation. 6 moles of aluminum would have 3 times 6, 18 moles of that. 3 times 2 is 6, and 3 times 3 is 9. It would have that many moles of everything. Now the problem said, how many moles of hydrochloric acid are required to react with 6 moles of aluminum? Well, look right there. There's 6 moles of aluminum. Problem says 18 moles of hydrochloric acid. We got the answer right there in the balancing coefficients. We didn't have to do any conversions and anything like that. We just rebalanced the equation and got the correct answer. Here's another one. Now, how many moles of hydrochloric acid are required to react with 5.4 grams of aluminum? Well, what do I want? I want 5.4 grams of aluminum. Well, the equation is showing 2 times 27 is 54 grams. Okay, that's 10 times too much. What I need to do, I need to divide through by 10. So I rebalance the equation. Now that 0.2 aluminum is 5.4 grams of aluminum. But when I did that, I got 0.6 moles of this. So how many moles of hydrochloric acid are required to react with 5.4 grams of aluminum? There's my answer, 0.6. I again got the answer by rebalancing the equation and reading off the coefficients of the rebalanced equation. I didn't do grams to moles and moles to moles. That's the way you would have done it from high school. I didn't do that. I did it this way. Now here's the general method. We're going to calculate a rebalancing factor. That's what I need to multiply through the whole equation by in order to get the quantity that's given in the problem to be what is shown in the balanced equation. So you calculate the rebalancing factor by taking the problem quantity, whatever's given in the problem, with the units given in the problem. We're going to divide by the equation quantity of that same substance, but in the unit that was given in the problem. You know, the equation has whole number coefficients. That represents moles. But if this quantity up here was grams, I would want this to be in grams, not moles. And we would then rewrite the problem to make that work. Okay, so you calculate the answer by just taking the rebalancing factor and multiplying by the equation quantity of the substance being asked for in the problem in the unit that was given in the problem. Now, we'll work some examples, and that'll make a little more sense. How many moles of hydrogen will form from reacting 8 grams of aluminum? Okay, here's my rebalancing problem. The problem gave me 8 grams of aluminum in the problem. I want to show the number of grams of aluminum in the balanced equation. Well, that's 2 times 27. So there is the amount of stuff in the unit given in the problem. There is the amount of aluminum, again given in the unit given in the problem. My rebalancing factor is 0.148. Now, what do we do with that? We're going to multiply that through the entire equation. So 0.148, but I'm going to focus on just what the problem asks for. I have to multiply it by everything, but I have to multiply it by the hydrogen, how many moles of hydrogen, and there's 3 moles. So the equation is showing 3 moles of hydrogen. If I multiply that out, that's my answer, 0.444 moles of hydrogen would form from 8 grams of aluminum. I did not go grams to moles, moles to moles, moles to grams. I rebalanced the equation to make it look like the problem. And then my answer was just the thing that's shown in the balanced equation. There's my balanced equation. 8 grams of aluminum is 0.296 moles of aluminum, 0.148 times 2. And 6 times 0.148 is that. And 2 times 0.148 is that. And 3 times 0.148 is that. So I got the answers. How many moles of hydrogen will form from 8 grams of aluminum? So there's my answer. There's 8 grams of aluminum. There is the number of moles that was needed by just looking at the coefficient in front of the rebalanced equation. Okay, now you want to make the average freshman chemistry student panic. Give them this type. This is called a limited reagent problem. The book would tell you to work these kinds of problems twice, work it with the 5.8 grams of aluminum, and then work it again with using 0.612 moles of HCl, and whichever one is smaller, that's the correct answer. That is correct. But why in the world on an exam would I want to work 2 problems when I can work 1? Look, let's do a rebalancing factor for aluminum. I had 5.85 grams of aluminum. The equation is showing 2 times 27. Don't forget that. If we're doing grams, we have to multiply by the atomic weight. My rebalancing factor on aluminum is 0.108. We've also got a rebalancing factor for hydrochloric acid. I had 0.612 moles of hydrochloric acid. The equation is showing 6 moles of hydrochloric acid. Divide that out, you get 0.102. 102 is smaller. That means that the hydrochloric acid is going to be used up. Once that's all gone, the rest of the aluminum can't react. So the amount of product or whatever is going to be determined by the limiting reagent, the one that is used up first. Okay, so this is our limiting reagent. Now, the answer then is going to be multiply that rebalancing factor through the entire equation, but I'm interested in this problem, what mass of hydrogen? Well, the equation is showing 3 moles of hydrogen and 3 moles of H2. Each one has 2 hydrogen atoms in it. The atomic weight of hydrogen is this. So it's 3 times 2 times this times my rebalancing factor gives me the answer, 0.617 grams of hydrogen. So this now is an easy way to do limiting reagent problems. We only work the problem through with the rebalancing, the limiting reagent rebalancing factor, whichever one of them is smallest. That's the one that you use in the problem. Now, I could, another really hard problem up here then would be how much of one of the reagents, which one, and how much is going to be left over when the reaction is done. Well, you see, I've already got that answer too. If I took 0.102 and multiply it by 2, that's how many moles of aluminum would still be left there. So I could then convert that to grams, subtract it from how much I started with. That's how much aluminum would still be there. So remember, that rebalancing factor multiplies the entire equation, and the amount used in this reaction is going to be contained in every single coefficient there. So not only do you do the one problem, you do the entire equation at once. And that's much, much better. So here we go. There is the new rebalanced coefficients. And like I said, if you take 0.204 times 27, that's the grams of aluminum you used, and you subtract that from 5.85, that's how much is left over. And I didn't ask for it, but there's how much aluminum chloride you're going to make. I might need to know that as a lab instructor, because maybe I want to treat that like a hazardous waste, and I want to know how big a container do I need in order for a lab of 40 to do that experiment. I'm telling you the honest truth. This is exactly the way Dr. Pearson does every stoichiometry problem I ever do. I absolutely never, ever use what you was taught in high school. This, and in most other classes here at MTSU, I'm sorry to say, but that's true. Theirs is the amount of materials. Now, here's a really complex reaction. This one might be a good one to end on. I'm going to just set it up and click through it, and then we'll finish up for today. And we'll come back to this on Friday. Okay? All right. Now, what mass of oxygen gas will form if 6.75 grams of peroxide is reacted with 12 grams of potassium permanganate and 0.25 moles of sulfuric acid? Textbook method, grams to moles, moles to moles, moles to grams, blah, 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 has to be done 3 times. Pick the smallest one. No, I'll be waiting, having a nice glass of Coke while you get over the finish line. I'm going to do it this way. Rebalancing factor is the mass of the peroxide divided by the mass shown in the equation. It's 5 times the atomic weight of hydrogen peroxide is this. Now, always do it like this. Don't write 5 times this number and stick it over on a piece of paper and copy all this stuff out. Here's what we're going to do. There's the rebalancing factor based on peroxide, and I calculated it first. All right, now let's do the permanganate. There's 12 grams. I want to put that 12 grams of permanganate. There's 2 of them. Add up the atomic weights, and it's 158 grams. That's the rebalancing factor for the permanganate, and it's smaller than that one, but we got one more to do, and I calculated it second. Now, 0.25 moles of sulfuric acid. All right, 0.25 moles. Now the equation is showing 3 moles. I don't need to multiply by grams because I'm in moles here, really. I multiplied grams here because I wanted everything in grams, and these two. I do this calculation, 0.0833. Now, these are my 3 rebalancing factors. This one here, of course, is limiting. But on my calculator, I can't get back to that calculation. It's gone off my screen, and I can't do it. You can on most new calculators. What I would do, I'm going to have to multiply everything through by this rebalancing factor, and it's not the answer that's in my screen. So what I'm going to do is go back and recalculate this, push equal. Now that number is in my screen, and I can now do the multiplication through the entire problem by that. So I multiply the limiting reagent rebalancing factor times the equation amount of oxygen, that's what it's asked for, in grams. So there was my rebalancing factor. It would be on my screen now. I would just say answer, or just times 5 times 2 times 16 essentially for the amount of oxygen. 5 times 2 times the atomic weight is 16. And I get this number. So there is the answer to this problem. But remember, I need to multiply, if I multiply everything in that equation by the rebalancing factor, this is the amount of every single substance involved in this reaction, in the amount that will actually be used. So if I wanted again to know how many grams of peroxide would be left over, I'm going to take 0.19 times the molar mass of peroxide and subtract it from 6.5 grams. That's how much is still left. If I wanted to know how much sulfuric acid is going to be left, I would just take 0.114 moles, and so I use 0.114. I could almost subtract that in my head. 0.114 from that would be how much sulfuric acid in moles that would be left over. So you see we've got everything in there. If we calculate these into grams, I did this just to show you that when we add up the mass of all the reactants and the mass of all the products, we do have to get the same number. Okay. Now, here's another problem. So again, we calculated the rebalancing factor before and how many moles of product. I just did this to show you these things are all additive. So if I want to, I don't have to calculate the moles of everything present over here. All I have to do is take the rebalancing factor and multiply it by the sum of 2 plus 1 plus 8 plus 5. And again, instead of having 1, 2, 3, 4, 4 things here, each with three steps, and 3 times 3 times 3 is 27, and 4 is whatever that is, 108 different problems. No way. This we can do all in one step. Okay, so there's my answer. And here's your checkpoint on this. And I believe this really is the end of what we're going to do for today. Okay, now we're a little bit over, and some of you had to leave. I'm sorry, but I will take this recording and upload it to D2L so that you will have access to all of this by the time we meet again on Friday. Do any of you have any questions before we stop the recording? All right, I do appreciate it, and I will see you all again on Friday.
Just a quick thing. Got something that popped into mind.
I'm sorry, I had already clicked the off. No, it's still going. What was the question again?
All right, on the one where you had to give you 1 second, going back to the original calculation where you times it by 3. Was it 3112?
Mm-hmm.
The problem that it had written down said you wanted to multiply it by 2113, not 31.
Oh, well, you know, that might be true. I'm not really sure. I didn't proofread this, and sometimes they do have some incorrect answers. So which problem was that?
Give me 1 second.
Let's see. Can I put this down? Okay. Have you found it yet, Ethan?
Not yet. Just I'm right now trying to go through and see if I can find it here. If I take too long, however, I believe given a little more time, I can track it down and email exactly which slide.
Okay, would you email me that, and then I'll fix it so that this doesn't happen again, okay?
That will work.
All right, thank you. All right, well, we'll see you guys then on Friday. And sometime before your class, I will probably invite you to just a brief meeting for questions if you've got them. If you're not able to meet at the time you get that invitation, you're in another class, whatever, then you can email me. But I just thought it might be good to have a little face-to-face office hour sometime in the day, either tomorrow or Friday, probably late tomorrow or early Friday morning. Okay? All right. Well, we'll see you, and you all have a good evening and the day, and may God keep you all healthy. Amen.
Thank you.